So thanks, Peter. So I'm going to tell you about one of the projects that we have in our group, which we did last summer with Yuan Julie, who was a visiting researcher, and who is also an assistant professor at CMU, and Dheeraj Nagaraj, who was my intern, and he's also a graduate student at MIT. So what we were trying to understand is what is the exact role of overparametrization for robustness in neural network? So let me tell you what the picture I'm showing here is about. So on the x-axis, I'm plotting the dimension or square root of the dimension. So I'm in a machine learning setting. I'm going to be in high dimension. I mean, here the dimension varies between something like 100 and 5,000, something like that. And the blue dots, they correspond to training a very, very large neural network to fit data in that dimension. And the red dots, they correspond to training a small neural network to fit the data. And what you see on the y-axis is how Lipschitz is a corresponding function. Okay, so the less Lipschitz it is, the less robust it is, the higher it is. And you can see the red dot, the small neural network, in high dimension, they are very non-robust. They are very non-Lipschitz. Okay, whereas the very small one, the blue dots, it remains basically constant, the Lipschitzness, as the dimension varies. So what we wanted to do in this project is to try to put this phenomenon on solid mathematical foundations. So here is what we did. Let me walk you through this. So I'm going to introduce a couple of notation, and really what the paper is about is a conjecture, and I will tell you some of the things that we know about this conjecture. So let me start with a definition. So first of all, we're only going to be talking about two layers neural network. Two layers neural network means there is one hidden layer. So what is a two-layer neural network? It takes as input a point x in Rd, in d-dimensional space, and it outputs the following number. So we're going to have k neurons. What each neuron does is that it first computes an affine function. So what is the affine function? It's parameterized by a vector WL and an offset, a bias BL. It computes WL.x plus BL. That's what the affine function of the else neuron does. Then it applies a nonlinearity psi. So psi is some fixed nonlinearity from the real line to the real line. Okay, so you can think of the rectified linear unit or the hyperbolic tangent or whatever you want. And so that's the output of the else neuron. Okay, so the nonlinearity applying to the affine function. And then the neural network recombines all these outputs linearly. So it does the sum for L equals 1 to k, and it recombines them with weights AL. Okay, and I'm going to denote this function class fk of psi. Okay, so this is a function that can be expressed as a k neurons neural network with nonlinearity psi. Now we're going to be in a machine learning setting. What does it mean? We're going to have a training set, a set of points xi, yi. Xi is the input, yi is the output. And for normalization purposes, I'm going to assume the xi's are on the unit spheres. They have unit norm. And the yi, I'm just going to consider binary classification. We can talk about more general things. So it's just a sign, either a -1 or a +1. And I have n points in d-dimensional space. And for this talk, I'm going to assume that this data is random, uniformly random. We can also discuss about this assumption, but for now, for this talk, everything is uniformly random. So whenever I say something holds with high probability, I mean with high probability with respect to the sampling of the data set, and I'm not going to precise whether it's exponentially large probability, polynomially large. It's not too important. So the first thing that I want you to know or remember is this theorem from 30 years ago by Eric Baum, which says the following. So the first question you might want to ask is, can I find a neural network that fits my data? Let's say that fits it exactly. Okay. So what it means is, does there exist f in fk of psi such that f of xi is equal to yi for any I in 1 to n? And what Eric Baum showed is that this will be true, this will happen, as long as the number of degrees of freedom of your function class, which is k times d, is larger than the number of equations you're trying to fit. Okay, so from your linear algebra intuition, it makes a lot of sense, but here it's a little bit different. So again, why is k times d the number of degrees of freedom? I have k neurons. Each neuron is described by d plus 2 points. Okay, the vector, the bias, and the recombination weights. Okay, so if k times d plus 2 is much larger than n, then you can find a function that fits exactly the point. Very good, perfectly understood. Now here is the question that we want to ask. Okay, so this is in a sense, this is the main contribution of the work. The question we want to ask is, what if in addition of these kind of linear equations, okay, by linear, I mean they are linear in the function in f, okay, in the estimation of, they are linear functional of the function f, they are just evaluation. So in addition to this n linear equation, what if we add also the very, very non-linear equation that the Lipschitz constant should be small? Lipschitz constant small means that we want our neural network to be robust. We want that if we input x and we get f of x, then if we input some, x tilde, which is very close to x, then f of x tilde should be very close to f of x. Okay, so it's a Lipschitzness is very directly a notion of robustness. And I didn't say it, but I'm always in this talk, I'm assuming that n as a number of data points is polynomial in the dimension. So if you take random points on the sphere, every point is far from each other. So it means that there exists an interpolation which is smooth. Okay, that's very, very easy to see. So there exists a function, which is not necessarily in fk of psi, which is constant Lipschitz and which fits perfectly the data. And the question we ask is, does there also exist such a function in fk of psi? Okay. And what's easy to see is that yes, the answer is yes, if k is larger than n. Okay, so if you have more neurons than number of data points, then you can actually fit smoothly your data point. And this is easy to see because what is going to be a smooth interpolation of your data point? Well, you just want to have a small bump around each data point. And you can mimic each bump like this with one neuron or with a constant number of neurons. Okay, so it's easy to see that when the number of neurons is larger than n, you can do it smoothly. And we said that when the number of neurons is larger than n over d, that's already enough to fit. So this k larger than n, it's an overparametrization by a factor d. Okay, so it's a huge overparametrization. And the question is, do you need this huge parametrization, or is there a smarter way to interpolate smoothly with neural networks? And the key point is our conjecture. So our conjecture says that basically you cannot do better than the trivial thing k larger than n, and that overparametrization is absolutely necessary for robustness. So mathematically, what we say is there exists if there exists a function f in fk of psi which interpolates your data such that f of xi is equal to y, then necessarily it must be that the Lipschitz constant, let's say even restricted to the sphere, but you can just think about the Lipschitz constant on the whole space, is larger than square root n over k. So let's parse this, larger than square root n over k. It means that if you want the Lipschitz constant to be O of 1, k needs to be larger than n. Okay. On the other hand, if you are the optimal size regime, if k is like n over d, then necessarily the Lipschitz constant is like square root d. So this conjecture fully justifies the picture we had. Okay, so I have 2 minutes now. So let me just, in 2 minutes, tell you the 3 results that we know, the partial results. So we have only 3 partial results. The first one is that this conjecture is actually true if instead of the Lipschitz constant, you compute a certain upper bound on the Lipschitz constant, which we call the proxy Lipschitz constant, which is basically the product of all the Lipschitz constants of the different ingredients of a neural network. So the first layer is a certain affine map. Then the second layer is a certain linear function, and in between there is a nonlinearity. So the Lipschitz constant of the whole thing by the chain rule is upper bounded by the product of the 3 Lipschitz constants. So if you look at the product of the 3 Lipschitz constants, then this is larger than square root n over k. We only know how to prove this for when there is no bias term. Another thing that we know, the second result, is the Lipschitz constant is larger than square root d over k for rectified linear unit networks with no bias. This is a completely different phenomenon. It looks like, oh, it's pretty good. Instead of square root n over k, you get square root d over k. But let me say this is completely different because it's only interesting when k is less than d, meaning that your neurons don't even span the whole space. So it's an undercomplete scenario. And the most interesting result is the third one, when the nonlinearity is a polynomial of degree p. Then we can actually prove the conjecture, and it's a nice proof which is related to deep mathematics about tensors. But we can only prove it in the case where n is as large as possible for such a psi, meaning that n is of order d to the p, and when k is the number of neurons is as small as possible, meaning that k is like d to the p minus 1 and n over d. So in this extreme regime, then we can prove the conjecture, and proving it, for instance, for other k is related to very, very difficult and interesting mathematics about low-rank tensors that I don't have time to get into. I think that's all I wanted to say. Thanks.